Good morning, everyone, and welcome to Quarks to Quasars, the flagship lecture series of Horizon, the Physics and Astronomy Club of IIT Madras. For the first session of the semester, we have Dr. Mansi Kasliwal from the Calfornia Institute of Technology. After completing her undergraduate studies at Cornell, she joined Caltech for her postgraduate work and later as a faculty member. She initially focused on supernovae and the mid-infrared sky, but with the advent of gravitational wave astronomy, she started working to search for the electromagnetic counterparts. Apart from her research work, Dr. Kasliwal is also actively involved in promoting educational reforms for underprivileged children in India. Over to you, ma'am. Looking forward to this great session.
All right. Good morning, everyone. Thank you so much for listening to me today. I have to say I kind of regret not being there in person because two of my very close friends from grad school when I did my PhD at Caltech are now professors at IIT Madras, and I had the pleasure of visiting them just a few years ago, and your campus is beautiful. But we'll do the best we can in this virtual format. And today, what I'd like to tell you about are cosmic fireworks. And you see my favorite cosmic firework playing in the animation in the background. And what you just saw was two neutron stars spiraling towards each other, merging, forming a black hole, literally the birth of a black hole, the launch of a relativistic jet, an ultra-relativistic jet with a Lorentz factor of 100. And then the formation of a cocoon, which is mildly relativistic. And then that cocoon breaking out, and then half the elements in the periodic table getting synthesized, just like that. Okay, so we'll go into some more depth about different fireworks, but I just wanted to put my favorite one out there before we go any further here. So let me also tell you what my favorite, since we're talking about favorite fireworks, let me tell you what my favorite part about being a faculty member at Caltech is. And that is this wonderful group of smiling faces. These are my students and postdocs that I have the pleasure and privilege of mentoring. And I have to confess, the reason I accepted this invitation is that some of my best students have actually come from India. So you see Kishale there, he's from IISc. Viraj is from the other IIT, the IIT Mumbai, not Chennai. And it's just wonderful to talk to students, especially undergraduate students, to see who's really interested in astronomy, listen to their questions, and see what their career goals are, and where they go from here. So my favorite part about Caltech is certainly these my research group, these students and postdocs that you see here. So today's lecture, I've organized it into three parts. Part one is how do we discover cosmic fireworks? And I hope this will appeal to the engineers amongst you. I also should tell you that I myself was an engineer as an undergraduate for probably the same reasons that some of you are. And I majored in engineering physics in the College of Engineering at Cornell University. So I'm very interested not just in the science, but also the technology. So I'll start with the technology that actually makes the science happen. Then in part two, after discovering the cosmic fireworks, I'd like to tell you about how do we actually characterize them, right? Cosmic fireworks are these brilliant flashes of light, but they're very short-lived. So you have this tiny window of opportunity in which to gather as much data as you possibly can to understand that firework, right? So it requires some coordination and being very organized to try to collect the data across the electromagnetic spectrum to characterize that cosmic firework. And then I'll spend most of the lecture on part three, which is the science, right? So after we've done the hard work of enabling the discovery and characterizing, what do we actually learn from these events? So let's begin with how do we discover them? And for that, I'd like to take you virtually to Palomar Observatory. This is my favorite mountaintop on the planet. It's absolutely beautiful, and there's so much history here. It's like the mecca of astronomy. So in the center, you see the Palomar 200-inch Hale telescope. And it's named in honor of Professor George Ellery Hale at Caltech. And when he built this telescope, it was just unlike anything else the world had ever seen. And it was unbelievable how it was put together more than 70 years ago now. And the motto of Professor Hale was make no small plans, dream no small dreams. And even though the centerpiece of the observatory is this beautiful Palomar 200-inch Hale telescope, the entire observatory lives and breathes this motto. So it's surrounded by what is called what I like to describe as celestial cinematography. So you see a lot of small telescopes in the vicinity, and I'll take you inside a couple of the domes today. But these telescopes are fully robotic, and they instead of taking a single image of the sky, they make a movie of the sky. So when we're looking at studying the dynamic universe, trying to understand what changes in the sky, find these really luminous explosions that are very short-lived, we need to be able to image the sky at a rapid rate. So we need wide field of view cameras and robotic telescopes. And the two domes that I'll take you inside today, one is the Samuel Oschin 48-inch telescope dome that houses the Zwicky transient facility. This is a wide field optical imager. And the other is a clamshell dome that houses Palomar Gattini-IR, which is the first wide field infrared surveyor. So I'll tell you more about both of these as we go along. So the Zwicky transient facility, now inside the dome of the 48-inch telescope, you see this Schmidt telescope. So Schmidt telescope is a telescope design which gives you a very fast focal ratio, right? So it gives you a very wide focal plane. Now, on this focal plane, Professor Fritz Zwicky, again, many decades ago, right? I mean, he pioneered this technique, this concept of time domain astronomy and discovering supernovae. But the way he would discover supernovae is that at the back of a Schmidt telescope, this was the 18-inch Schmidt telescope, he would put a photographic plate and very, very carefully, take those exposures, go develop those photographic plates in the dark room, take some more exposures, go and develop it in the dark room in the same dome. And it was a very difficult process by which supernovae were discovered. Now what we've been able to do, thanks to Moore's law and advances in semiconductor technology, is that we've been able to afford wafer scale devices. So now not only do we have CCD cameras that are 1,000 pixels by 1,000 pixels, but we actually have entire wafers, and you see these wafer scale, 16 of these wafer scale devices on the bottom right there. So that entire focal plane has been filled with silicon. So in one shot, in one 30-second image with the Zwicky transient facility, we're able to image 230 full moons. So let me explain to you what that means, right? So I'm emphasizing here that the key metric is what is the field of view of the camera, right? I mean, how much of the sky can it image in one shot? Because that tells you how quickly it can image thousands of square degrees over and over again, right? So that gives you what is called the volumetric survey speed or the sensitivity to transients, right? So here you see just a collage of different optical detectors, right? I mean, thanks to this CCD revolution, lots of people are trying to build different wide format detectors. My own thesis, which was about a decade ago now, was what you see as PTF on the bottom left there. That's the Palomar Transient Factory. And, that was a beautiful camera back then. It was 7 square degrees. And it was on the same telescope that I just showed you, the 48-inch telescope. And just a decade later, I'm telling you about a camera now, which is 47 square degrees, right? So then beautiful Andromeda galaxy fits in, one little chip there, right? So it's quite remarkable because if you're imaging 4,000 square degrees an hour, which is the speed with which we can image the sky, then you run out of sky to observe in a few hours, right? Because think about it, you're looking at the sky above, you want to look at reasonably good air mass. So there's only about 15,000 square degrees or so of good sky to observe. So if you have such a fast imager, you can image huge spots of sky multiple times a night, night after night. And what this has meant is that if we are able to take this fantastic data stream, and now I appeal to those of you interested in data science, machine learning, computer science challenges. This is a major data science problem. We have a huge volume of data that we need to process within minutes, right? Because we're looking for the fastest fireworks in the sky. How do we find them? So we do image subtraction, and one would think that even my 5-year-old knows everything there is to know about subtraction. He was very surprised when I explained to him that he really doesn't yet know what is subtraction. So in this case, when you're subtracting images, there's a complication, right? Because if I want to subtract 2 images to see what has changed, I need to match the images very, very well. And that's a much tougher problem than you think, because every time you point your telescope, the photons fall on a slightly different part of the detector, right? So you need to correct for those pixel by pixel differences. Every time you take an image, the speed at which the wind is blowing is different. There might be a few clouds or not, right? And all those differences change your point spread function. So it's a little bit more complicated to do the image subtraction than one may think at first blush. But we have some excellent algorithm progress just in the last few years, actually, on how to do proper image subtraction and how to maximize the signal to noise in those subtracted images, and do this in a fully automated, very efficient manner, such that completely robotically, you're able to flag and identify a flash of light in the sky that wasn't there the night before. And this can be all done while me and my graduate students are fast asleep, which is a relief. And just to put this in context, right? I mean, a decade ago we would celebrate every supernova, right? We would know its name and we would know everything there is to know about it. Now we are talking about thousands of supernovae. So in just a couple of years with this Wiki Transient facility, we found over 5,000 supernovae. And what you see in the different colors are the different flavors of supernovae. So if a white dwarf got completely obliterated, that's shown in red. If it's a massive star, that's a type 2 explosion, right? A massive star that underwent core collapse and then exploded, you'll see that in blue. And some of you may have a very good eye and may notice some green dots. Those are what we call superluminous supernovae. So supernovae are typically 1 billion times the brightness of our sun when they explode. These superluminous supernovae are tens of billions of times the brightness of our sun. And if you ask me a question, I can tell you more about superluminous supernovae and what we learn from them. And on the right, you see a 3D rendition of the same supernovae as well. Okay, so now I want to change gears a little bit and switch from visible light, which is the light that your eyes and my eyes can see, and dial up the wavelength a little bit and talk about infrared light. And one may ask, okay, why would looking at lower energy, why would looking at longer wavelength, right? What do lower energy photons tell us that that visible light does not, right? And to motivate that, I'm showing you a picture of a piece of our own galaxy, the Milky Way. And if you look at it, you'll wonder why I'm talking about this picture for so long, because there's not much there, right? I mean, there's some stars, that's fine, and there's a big dark blob. The reason I'm emphasizing this is that it's just a matter of perspective, right? This is an image in visible light. You increase the wavelength, you're able to go around the dust with the infrared wave bands, and voila, you can see that in the star cloud, there's actually a protostellar jet that's being launched, right? So the young star erupting and launching this protostellar jet. So there's a lot more than meets the eye, if only you're willing to tune your wavelength a little bit longer. So this picture, and pictures like this, studies like this, motivated me to try to do time domain astronomy in the infrared. But I'm showing you again, the collage of optical cameras out there, because as I hope some of you would appreciate that, silicon has a band gap at 1 micron, right? So you cannot use CCDs beyond 1 micron. So you cannot use this wafer scale device technology to build your wide field infrared camera. So you're stuck with things like mercury cadmium telluride or indium gallium arsenide, right? So you have to either look at the columns 3 and 5 or 2 and 4 in the periodic table to be able to push to longer wavelengths in the infrared. And these are extremely expensive. So pixel by pixel, there's just not been as much of a revolution in infrared cameras as in optical cameras. So when I joined Caltech as a faculty member in 2015, the biggest infrared camera out there was this very expensive European camera called the Vista camera. And its field of view was 0.6 square degrees, right? Just about one full moon, not 230 full moons. Now, I wanted to build something that was a scale of ZTF in the infrared, right? What I wanted to really do is make that leap to wide field in time domain astronomy in the infrared. And the way I did that is by using advances in both software technology and detector technology. So I'll tell you more about both now. And the project I want to tell you about now is Palomar Gattini-IR. So I couldn't quite get 47 square degrees, but I got a whopping 25 square degrees, which is still more than 40 times larger than Vista. And what I did was use this, at first I was inspired. Whenever you're trying to make a leap by a factor of 40 or like try to do something that hasn't been done before, it's good to have some inspiration, right? And in this case, Caltech was a good place to be because everything we basically know about infrared astronomy, Caltech is one of the birthplaces for this. And there were people like Professor Neugebauer, then Professor Layton, then Professor Seufer, like a whole series of people who basically developed this field from a 1-pixel infrared detector at the 200-inch telescope to, the arrays that we're working with today. So it's a good place for inspiration, and especially when making these leaps of faith, it's good to have some good mentors around and some inspiration in the worlds does help. So with that, we built something called Palomar Gattini-IR, and you'll see this 30 centimeter telescope there, and the trick is that it's a very fast focal ratio. So if you take the focal distance and you divide that by the diameter, that's a small number. And what that gives me is a very large angular field of view on the sky. And at the back of it, I just put one detector, one 2K by 2K detector, because that's all I could afford at that time. So each of those pixels subtended a very large area on the sky. So each pixel subtended 8.5 arc seconds on the sky. Compare that to the Zwicky transient facility, which is only 1 arc second per pixel. So what I was going for was coarse spatial resolution, but a very large field of view, and using software technology. So when I went and took an image, I would use software technology to regain that spatial resolution. So let me explain how I would do that. So I would go, what I do is I point the telescope to one piece of the sky, take 1 8-second exposure, and then I make a small dither, take another 8-second exposure, small dither, and take 8 of these 8-second exposures, right? So every time I do that with these small dithers, the star falls in a different place in the chip, right? And it leaks light to its neighbors in a different fraction. So you can literally use that to do what is called drizzle the images and get half arc second accuracy on your astrometry. And with that, you now have the tools to discover infrared fireworks, right? So I'll show you some more about the discoveries from Palomar Gattini-IR in part 3. But in order to understand what we discover, right, what are these flashes of light, we need to characterize them by collecting data across the electromagnetic spectrum. So you can have your optical discovery engine, you can have your infrared discovery engine, but you need to combine all of that into characterizing those transients across the electromagnetic spectrum. And you have to do that before they fade, right? So, okay, it's all well and good that we make the discoveries at Palomar Observatory, but then the sun rises at Palomar, right? So we cannot do this alone. We cannot characterize transients on one mountaintop. It's just not possible. So in order to beat sunrise and look for transients that fade on few hour timescales, what we do is we built a relay of observatories, a network of observatories around the world. And we just keep moving west, right? So this is like taking advantage of this jet lag and this time difference here, right? So west of Palomar is, of course, Pacific Ocean. In that, there's the beautiful island of Hawaii. which has, the magnificent Keck telescope, Gemini Observatory, many other telescopes on that mountain. If you move further west, then there's Japan, Taiwan, India, Israel, and Sweden. And here I'm marking the partners. I mean, there are many other countries, right? But I'm marking here the partners in the growth network. So growth is an international collaboration that is a partnership in international research and education. And India, in particular, has been a fantastic partner, right? And there's a brand new telescope called the Growth India Telescope that Professor Varun Bhalerao at IIT Bombay and some of his students deployed at Hanley. And that's been collecting great data for us as part of this network of observatories around the world. So I'll show you some of the results from the growth team as well in part 3, but you need this sort of systematic coordination, right? And I was talking to you about thousands of supernovae now, right? There's just no way to remember the right ascension and declination and which one needs data from which of these telescopes in any sort of systematic way, right? So for that, again, we developed a tool which we call the Growth Follow-Up Marshal, which is a completely dynamic and collaborative platform. So it's literally our Facebook page, right? I mean, I know all of you have a Facebook page for Horizon. This is our Facebook page, but it has, all the information we need about which supernovae are being discovered, which transients are fading very quickly, which ones need follow-up with which telescope, what is the latest thinking about the transient on that day, which is the most viewed transient, right? That means there's a lot of activity, lot of excitement there. So that when we sit down to write a paper, when we sit down to say, okay, now what did we learn? We have all of the data organized in the central database, right? So it's both triggering, it's taking the input from the discovery engines, it's triggering the robotic follow-up telescopes, and it's collecting the data back from these follow-up telescopes and organizing all of this into the central database and web portal. Okay, so now let's move on to part 3, which is we've discovered a whole bunch of cosmic fireworks, we've characterized them, we've done the hard work here. Now let's do the fun part, which is what do we actually learn from them, okay? And for this part, I want to again break it up into a few sections. So I want to take you back to the life cycle of a star. So I know many of you are astronomy enthusiasts, so I hope you would, some of this would be familiar to you, which is that, I mean, if you think of a stellar cloud, it collapses. It forms a whole bunch of stars and distributed by the initial mass function of a star, right? The many sun-like stars, very few very heavy stars, right? It's described by something called the initial mass function. Now, a sun-like star would expand. It will live a very long life. Like a sun itself will live 10 billion years, right? Then it'll expand to form a red giant and then eventually end its life as a white dwarf. Now, white dwarf is a very dense object, right? But it's also a very long-lived object. Okay, so we'll come back to white dwarfs in a bit. Now, if you have a more massive star, let's say take a star, say 10 times more massive than the sun, instead of a red giant, you'll form a red supergiant. And then when the star will go further in terms of nuclear burning, so not only will it burn hydrogen into helium and helium into carbon, nitrogen, oxygen, you can keep going there, right? It will burn silicon, sulfur, it'll go all the way up to iron, to the point where in additional burning of fusing of elements in the core is just not exothermic. It's just not efficient and energetically to fuse anymore. At that stage, this massive star in like about 10 million years or so will run out of luck, and the core of that star will start to collapse. Okay, and when the core collapses, you would get this brilliant explosion, which is a core collapse or a type 2 supernova. And depending on the details here, that supernova could either form a neutron star, or it could form a black hole, or there could be pair annihilation and you could get no remnant at all, right? If you have pulsational pair instability. So you have these 4 different outcomes for the star, depending on what its final fate is. And I really want to focus on that right column there, right, of the outcomes. Because if you had a mythical teaspoon, right, and you're able to scoop out 1 teaspoon of a white dwarf, the white dwarf is so dense that 1 teaspoon would weigh a few tons, right? In fact, a white dwarf cannot even support itself just by gravity alone. It needs the quantum mechanical electron degeneracy pressure to balance gravity just for the white dwarf to hold itself together. And so it's extremely dense. All kinds of fun things are happening in a white dwarf. And in particular, if you pair the white dwarf with another companion, you could get a whole bunch of fireworks, right? Now let's go to the neutron star. Now here you dial up the density by many more orders of magnitude. So that same teaspoon that was a few tons for a white dwarf is now few million tons for a neutron star, right? So it's much, much more dense than a white dwarf. And you're in the regime of neutron degeneracy, not just electron degeneracy. Now, black holes, of course, are singularities, so it doesn't make sense to put your mythical teaspoon in it. But we're now talking about environments which are extremely dense. So you can really see strong field gravity at play and extreme states of matter. So you have an opportunity to understand things, and these are laboratories just unlike any other. When you're studying these fireworks, you have access to a lab, right, that you cannot imagine in your wildest dreams having here on planet Earth, right? So now let's talk about fireworks in each of these three categories: white dwarfs, neutron stars, and black holes. Okay, so let's begin with some white dwarf fireworks. So let's begin with some light curves from the Palomar Gattini-IR project. So I described to you this infrared camera. So let me tell you what is a light curve. A light curve is just brightness as a function of time. So I'll show you light curves of many different shapes and varieties now, but it's always brightness as a function of time. Now, astronomers quantify brightness in somewhat complicated units. I mean, we have this arcane system of magnitudes, right, which is minus 2.5 times log of the flux, right? So smaller numbers actually brighten, okay? But don't worry about that. Just think about this as brightness as a function of time. Now, in these light curves, you see these light curves here. So Viraj would describe these as roller coaster light curves, right? Because you have a star that's disappearing for months on end and then coming back. And this range here, right? I mean, if you have 5 magnitudes, that's a factor of 100 in flux. So it's a very significant reddening. And what these things are light curves of are Corona Borealis stars, right? So the prototype is a star in the constellation of Corona Borealis. I hope some of you at least are amateur astronomers and know your 88 constellations. You can't see all of them from Chennai, but at least some of them. And Corona Borealis is a very easy to identify constellation in the sky. And one of the first variables found in it was a prototype of this class. What these things are thought to be, and there's still some debate in the literature as to their origin, is white dwarf merger. So two white dwarfs merging to form a heavier white dwarf, but not exploding in the process, just forming a stable, heavier white dwarf. But there's so much material being dredged up and down that this is a very dusty, very red phenomenon. So the dust actually causes these long dimming events and the star disappearing for a while and then coming back. Now, that's okay, but sometimes a white dwarf gets greedy, right? Sometimes if a white dwarf is stealing material from its companion, then you can see, as you just saw there, right, that you might accrete so much material that you can no longer balance gravity and electron degeneracy. And ask me if you don't know what is electron degeneracy, just ask me what that is and I'll explain that to you. But if you have too much material that you've stolen, then you could have the entire white dwarf obliterate and explode, and that's called a type 1a supernova. So that's what the Nobel Prize in Physics was given for a few years ago, is using type 1a supernovae as standard candles for cosmology. Okay. So let's talk about white dwarf explosions next. And here I want to highlight some work by Kishale, which is to discover classical novae in our own galaxy. So now you can see, I showed you this image triplet, right, of A minus B equals C before for ZTF. Now you can see how much harder it is with Gattini, because in the infrared you have this bright sky background. And with Gattini, we had to give up on our spatial resolutions. We have these big pixels, which are quite difficult to subtract, particularly in crowded fields. But classical novae are so bright. Classical novae, now remember, I just explained to you what is a type 1a supernova, right? So the difference between a supernova and a nova is a supernova is 1 billion times the brightness of the sun. The white dwarf is completely destroyed. And a nova is 1 million times the brightness of the sun. And it's a small thermonuclear runaway on the surface of the white dwarf that doesn't destroy the white dwarf. In fact, novae can happen again and again on the same white dwarf and with the same companion because it's not completely destructive. So in the fastest of cases, you can have a recurrent nova with a time scale of 1 year. So every year you could have a nova eruption. But more typically, it's something of the order of 10,000 years at which the nova repeats itself. Now, in this case, these couple of examples here are classical novae in our own galaxy, in the Milky Way. So they're very, very luminous. They're 10th magnitude in their infrared, if that means anything to the astronomers in the audience. And the same nova is extincted by 8 to 10 magnitudes in the optical bands, right? So you can see it's down at 18th mag in the optical bands. So these are novae that are just buried in dust, right? And they're buried in the dust of our own galaxy. So if you're now looking at the Milky Way, so if you go out and you look at the night sky, you see this band, right? Which is the Milky Way. That's the plane of the galaxy. In yellow, I'm blocking out the southern quadrant of the galaxy. And before Gattini, novae were found all over the Milky Way. They're shown by these blue dots. These are discovered over many decades. You see that compilation there. With Gattini, in just a couple of years, we're finding novae in the plane of the galaxy. That's where the stars are, right? So it's no surprise. But these novae that are in the plane of the galaxy were hidden from view for optical searches because they were so red that the dust just made them appear to be very, very faint, right? So this is, again, no surprise, but it just hadn't been done. And it's important to quantify this, right? So there's a nova guru, right, whose name is Bob Williams. And when he saw this paper that Kishali wrote, he sent me this lovely email where he told me that he's often wondered where these classical novae are, right? Like Fermi wondered where intelligent life was. And the missing novae are actually just extincted. They're in the plane of our galaxy. So what Kishali was able to do in this lovely paper that he just wrote in January, actually, is compute the extinction distribution to find out how red are these novae, right? So in the optical, you get one distribution. In the infrared, you see there are many more that are redder because you're sensitive to all of them, right? Not just the ones that are not reddened. And so you can now infer that the rate of classical novae is 46 plus or minus 13 per year. And this was a very welcome number, very welcome calculation by the NOVA community. And I got really many emails about how much people are enjoying reading this paper, which was a lot of fun. So that's what I wanted to share with you today about white dwarf fireworks. Now we're going to change gears a bit and talk about neutron star fireworks. Okay. And for this, I'm going to take you back in time to August 17th, 2017. So I'm going to take you back to actually what I showed you in the first slide of the lecture today, which is the two neutron stars merging to form a black hole. Because honestly, this piece of the lecture used to be this crazy dream, this thing that will happen one fine day. This thing that people now call multi-messenger astrophysics, where you're combining information from different messengers. Even when I joined Caltech, I wrote in my application that this is what the research that I want to do is I want to do multi-messenger astrophysics. And some very senior faculty were like, okay, this is a good dream, but will it actually, what time scale will this actually be realized on? And I don't think anybody had predicted that would be, 2 years. Okay. So this is quite a spectacular discovery. So let me tell you a little bit more about it. So on August 17th, 2017, at 12:41:04 UTC to be precise, right? Two neutron stars merged to form a black hole, and they emitted gravitational waves that was the loudest signal that the gravitational wave interferometers had seen to date. Now, I joined Caltech in 2015, so 2 weeks later, on September 14th of 2015, the first black-hole merger was detected by gravitational waves. So it was the first direct detection of gravitational waves, and in fact, that is what the Nobel Prize in Physics was given to my senior colleagues, Professor Kip Thorne, Professor Barry Barish, and Professor Ray Weiss at MIT. So the black hole discoveries were very stimulating. They were very groundbreaking, but they were very short-lived, right? Because the duration of that gravitational wave signal depends on what the density is. And some of you may know dynamical timescales, 1/√0. And so the black hole mergers were 3 seconds, 5 seconds, depending on the mass of the black holes, right? In the case of the neutron stars, now you're dialing down the density by quite a bit. So the signal lasted nearly 100 seconds. So it was the longest and the loudest signal that the gravitational wave interferometers had seen. And what was most amazing about it was, at least from my perspective, is that 2 seconds later, right, or 1.7 seconds to be precise, there was a 2-second burst of gamma rays that was detected by the Fermi satellite and the integral satellite. So within a couple of seconds, this became definitionally a multi-messenger event, right? You were seeing light and gravitational waves from the same source, right? And this was just amazing, right? I mean, usually every time LIGO detects a gravitational wave event, the entire growth team's, cell phones ring, because we're responding to these gravitational wave triggers to search for electromagnetic light from them by slewing our telescopes, doing all this work. And this time, I mean, we got the notification for the gravitational wave merger and the gamma rays within seconds, right? So this was the most amazing, notification to wake up for. This was, about 4 a.m. In California. And now that we have light from the source, we wanted to even localize it and find light in the rest of the spectrum, right? So as fantastic as gravitational waves and gamma rays are, they are, the chance coincidence of the timing was so small that we knew they had to be connected, they had to be related, but we didn't know where in the sky this had happened, right? So we didn't know the location in the sky. It was somewhere like within something like 30 square degrees, which is a huge area of sky. Lots of things can happen in that 30 square degrees. So immediately they began a search to look in these large error ellipses at these, 45 galaxies that were inside them to find the true home of the merger. And this finding of the true home of the merger converged on this one galaxy called NGC 4993 that was only 40 megaparsec away. So in case people don't know what is megaparsec, that's about 120 million light years away. So it's literally a backyard, right? This is very, very close in distance. And we now knew exactly which galaxy and where in which pixel of that galaxy, right? But to sub-arcsecond precision, we knew where the neutron stars had merged and where that black hole was born. So the coordinates were first announced by the Henrietta Swope 40-inch telescope at Las Campanas Observatory in Chile. And immediately there began the most magnificent campaign to characterize and collect data about this particular transient. So you see a movie here about, how time is ticking, the sun is setting in different parts of the globe, different telescopes are lighting up, collecting data, to give you a visual, right? Because there's something like 70 telescopes and 3,500 astronomers involved in this campaign. And there are even 7 telescopes in space, right? Where you don't even care about day and night. And you'll see some dots, some telescopes in red and some in green. And I challenge you to tell me what are the telescopes in green, because if you have a careful eye, you'll notice that the telescopes in green can collect data in the daytime. So tell me what kind of telescope that is, okay? So for 3 weeks or so, we didn't sleep. The growth collaboration, we were just too excited. We were just trying to understand what is it that we have just all discovered and what are we learning from all of this. So in those 3 weeks, I mean, unfortunately, after that, the event was at 13 hours RA, right, ascension in August. And I hope some of you can do a quick calculation and tell me that's not, a good place to be in August, because that's very close to the sun. So in a few weeks, unfortunately, this event became too close to the sun and we couldn't quite continue the campaign of studying it. But in 3 weeks, we had enough data to write 3 beautiful papers in the Journal of Science. And we focused these 3 papers sort of on what we were learning from the wavelength, from each of the different wavelengths, right? So the Evans et al. Paper focused on the ultraviolet and the X-rays. I focused on the optical and the infrared. My colleague, Professor Greg Hallinan, wrote a paper about the discovery in the radio. And then I'll tell you more about what we learned from these papers next. So there are 2 questions that this one firework could answer. One is nucleosynthesis, right? Which is, are neutron star mergers indeed the long sought sites of heavy element production? So for that, I want to take you back to your chemistry class, right? And the periodic table that I hope all of you know and love. And color code this periodic table as depending on where those elements are made in the universe, right? So most of the universe is pretty boring. It's just hydrogen and helium. It's made during Big Bang nucleosynthesis, so no big mystery there. The stuff that you see in blue, in light blue and dark blue, that's the stuff that's made in supernovae and in the cores of massive stars, right? But that only fills the next few rows of the periodic table. What we didn't know until August 17th, 2017 are all the elements shaded in yellow, right? So these are half the elements in the periodic table, heavier than iron. They were supposed to have formed, and we knew this back from the Burbridge, Fowler, and Hoyle paper in 1953. So more than half a century ago, right? That they are formed by something called R process nucleosynthesis. So the letter R there stands for rapid. And what's rapid about it is that it's a rapid capture of free neutrons to make heavier and heavier nuclei. Okay. So these very heavy nuclei are supposed to form by this process called R process nucleosynthesis, but we hadn't seen in all these 5,000 or thousands of supernovae that we had discovered any evidence of R process nucleosynthesis. So we hadn't seen any evidence by which these very heavy nuclei are forming, and it is not surprisingly at all. People had predicted that neutron star mergers will be a good place to find an abundant supply of free neutrons. So they would be a good place to go and find the signature of R process nucleosynthesis, right? Now the challenge is that when you form these very heavy nuclei, think about an electron that's inside one of these nuclei, right? So let's take say element number 57, lanthanide, right? So that will have you're now filling electrons not only in your S shell but also your P shell, D shell, F shell, right? And think back to all the different possible line transitions you would have. So you would have a G factorial in the denominator, right? So if you're already filling out your F shell, you would have a 14 factorial there, right? So, and then if you work out the numbers more precisely, you'll realize that there are millions of possible line transitions for any electron in these heavy elements. So now if you have radioactive decay and a photon that's escaping is trying to make its way from the neutron star merger to your telescope here on Earth to detect it, that photon will have lots of distractions, right? It could get bumped around by any of these electrons and get lost on its way here. So the emergent spectrum is actually peaking in much redder, much longer wavelengths. The emergent spectrum peaks in the infrared. So the way to find these signature of R process nucleosynthesis, the hallmark signature, is to look for rapid reddening. So look for infrared light here. And much to our amazement, that's exactly what we saw for this event GW170817. So in this majestic campaign, you can read many, many papers about the data from the light curves from this one event. You'll see that the blue light just disappeared very quickly. The ultraviolet disappeared in a few hours. The optical disappeared in a few days. And the infrared just lived for several weeks, right? So that meant that that flash of light rapidly reddened at an unprecedented scale, unlike anything we'd seen before on any other transient discovered then. Actually, in fact, it was almost a surprise that we saw any blue light at all. You don't expect blue light from our process nucleosynthesis, but we'll come back to why we see blue light at all. And now if you take that light coming from the merger and you disperse it through a prism, you see what's called a spectrum, right? And a spectrum is the chemical thumbprint. It's really a unique identifier for the explosion because it tells you what was actually synthesized by that explosion. And you can see in this case, right, this is a time series collected by the ESO VLT telescope. It's quite, this is from paper by Elena Pian here. And you can see all these bumps and wiggles in the spectrum, and they are telling you what elements are being synthesized. So there's no question, if you look at the light curves and the spectrum, that the heavy elements were synthesized, right? The debate then is whether or not those heavy elements are the same as the heavy elements that you see in the solar neighborhood. Are neutron star mergers the site, the one and only site of our process nucleosynthesis, or are they one of many sites, right? Because if they're the only site, then they should produce elements in the same relative ratio as we see right here on Earth, right? And this is a hotly debated topic, right, on whether what the answer to this question is. They seem to, if you do it on the back of an envelope, they seem to form like 10,000 Earth masses worth of heavy elements. And they happen something like 500 per gigaparsec cube per year. So if you multiply the rate by the amount that each one produces, it's roughly correct, right? So they're a very viable site for our process nucleosynthesis. But whether they're the only site and whether they produce, how much of which element do they synthesize is very debated. So one way to address that question is to look at the fraction of electron heating, right? We're looking at things that are species that are radioactively decaying. We know what the radioactive half-lives are. So we can compute what the fraction of electron heating is as a function of time. And there's something very interesting about that, which is that the lighter of the heavy elements in the first row of those yellow elements, with atomic mass numbers between something like 80 to about 120 or so, all of those elements dominate in the first month after explosion. So that's that green line that you see here. But later, between a month and say 3 months after explosion, it's only the heaviest of the heavy elements that dominate. Okay, so they might be in small fractions, small quantities, but they dominate at late time. Now, remember I told you that this was a right ascension of 13 hours in August, right? So it's a wrong place to be. So ground-based campaigns could not look beyond a month. It was just not practically possible given the location of the sun. But there's one telescope, and this is NASA's great observatory, the Spitzer Space Telescope, that was able to indeed look very close to the sun. It's in an L2 orbit. And it was able to image this event, the same galaxy, NGC 4993, at 43 days and 74 days after merger. And it was able to do this in a very red sensitive band. It has what is called an IRAC camera. And what I'm showing you here are images at 4.5 micron, right? So very far into the infrared. And these images, if you again do image subtraction with them, which is very difficult in the mid-infrared for such a bright galaxy, you actually cleanly recover the light from the gravitational wave event. And this detection of light at this very late phase tells you that not only were heavy elements synthesized, but even the heaviest of the heavy elements in the second and third peak were synthesized. And that includes elements like gold and platinum. And so, media and press releases got a huge kick out of realizing, that, it's not only most of the periodic table, but it's also things, precious elements like gold and platinum that are made in these neutron star mergers. Okay. And in particular, you could pinpoint these 8 elements, which could be responsible for that late time Spitzer Space Telescope mission. So now, in the last few minutes here, let me tell you a little bit about the jet physics, and in particular, this question of are neutron star mergers progenitors of short-hard gamma ray bursts? Okay. So I told you about what we learned from the optical UV optical infrared, right? So now we're going to look at the gamma rays and the X rays on the highest energy end and the radio on the lowest energy end for the same event. Okay. So this is the question of whether we saw a gamma ray burst or a burst of gamma rays. And this had us, scratching our heads for a very long time. So let me try to break this up into a few pieces to explain, right? So I told you everybody was just absolutely, excited and by this detection of gamma rays that were 2 seconds in duration. So it's a very short duration burst of gamma rays. But there was one problem, right? Once we identified that the galaxy was only 40 megaparsec away, it turns out that the luminosity of the gamma rays, the intrinsic brightness of these gamma rays was actually very low. So gamma ray bursts have also been discovered now by the thousands. But they are very, very luminous explosions that are typically discovered in galaxies far, far away. This particular one was so close that it actually was quite wimpy. It was a factor of 10,000 times weaker than any other gamma ray burst that we had discovered, right? And if you're looking down the barrel of the jet, there's just no way for such a weak burst to be able to break out and to be detectable, right? So we knew that this picture of looking down the barrel of the burst was wrong immediately, right? From on day one, people knew this just could not be. Now, let's say, okay, if you're not looking down the barrel of the burst, you're slightly off axis, right? So you're looking a little bit from the edge, and that's why you're seeing a weaker burst. And if you do work out the physics, you'll find that angle, right, that delta theta in radians, goes to the 4th power. So it's 1 over delta theta to the 4th power. So if you're 0.1 radians off, you would be a factor of 10,000 times weaker. Okay. So that's well and good. Okay. That at least solves one headache about, why the gamma rays were so wimpy and so faint. But there's a bigger problem, right? Which is that if you take this picture where you're only 0.1 radians off, you cannot explain the X-rays in the radio. So my good friend, Professor Greg Hallinan, had to patiently wait for 9 days, right? I mean, he kept observing with the VLA over and over again, very, very large array. This is in New Mexico. And he could not detect any radio emission until the 9th day, right? And he'd almost given up. All the other teams actually had stopped observing because they thought that maybe there's just no radio emission from this event. But Professor Hallinan persisted, right? And he was able to detect it, but only 9 days after burst. So this is an eternity in the life of a gamma ray burst. So if you just look at the radio data and you try this off-axis angle calculation, and when would you see the radio data and how off-axis do you need to be to have to wait so long, it suggested that we were way off-axis. Okay. Now, there's no way to have 2 lines of sight, right? So far, we still live on one planet Earth, and our satellites are not that far from us. So we cannot have 2 such wildly different lines of sight for 2 different wavelengths, right? We don't have telescopes on other planets and around other stars just yet. So how do we reconcile this conundrum, right? So we have the gamma rays and the radio and X-rays just not working with each other. So the way we solved this was by something called the cocoon breakout model. And what this is that you have the 2 neutron stars merge, you form a black hole, you launch a jet, but then the jet gets stuck, right? Because when the neutron stars were spiraling around each other, they were throwing out so much material around them that the jet was being launched not in a clean environment, but in a very big mess, right? So the jet actually transfers its energy to the surrounding. And then this entire wide angle cocoon, which is mildly relativistic, and by mild, I mean 0.99 times the speed of light, not 0.99999 times the speed of light. And then this wide angle cocoon, when it breaks out, naturally explains the fact that your gamma rays are weaker because it's slower. And because it's slower, again, you can very easily explain the delay in radio and X-ray emission. And in fact, by Doppler boosting, you can explain that first surprise, if you remember, that about the bright blue emission, because some of those infrared photons could just be Doppler boosted to the optical. So then the only question is, okay, there's all this, this cocoon definitely broke out. That explains all the early time data. But did the jet survive, right? Did someone somewhere on an alien civilization, assuming they had a telescope, would they have seen a gamma ray burst, an ordinary short-hard gamma ray burst? And it turns out the answer is actually the jet did survive, but we didn't know this until like 200 days later, when we saw the radio light curve peak and then decline. So in the interest of time, I'm actually, I was going to tell you a little bit about black hole fireworks, but I'm quite eager to hear your questions so far. So I'm going to skip forward, but feel free to ask me about this if you want to know. So in terms of black hole fireworks, I was going to tell you something about neutron star black hole mergers, and then this idea about building a telescope in Antarctica as well. But I'd like to actually stop here and take questions, and we can come back to this if there's interest later in the talk. Okay. So thank you, Vivan, and I'd like to take questions now.
Thank you, ma'am, for that wonderful talk. The first, could you please elaborate on the superluminous supernovae?
Sure. So superluminous supernovae are, as I mentioned to you, they are super, right? There's another prefix to it because they're nearly 10 billion times the brightness of our sun. So they've just been discovered in the past decade, but they're a steadily growing population. And what these are thought to be are magnetars, actually. At least some of them are thought to be magnetars, where the typical magnetic field of the neutron star is actually boosted by the dynamo effect. So you could have magnetic fields of the tune of 10 to the 15 Gauss in these events as well. And these very luminous explosions are either sometimes attributed to magnetars or sometimes attributed to pair instability, pulsational pair instability, where you could have lots of electron-positron pairs annihilating and completely destroying the star in that way. And if that's preceded by pulsations, violent episodes of mass loss, then you could get these exotic superluminous supernovae.
The next question we have, ma'am, is how exactly a difference image is able to identify the presence of a transient source in the field of view of the camera?
Yeah, now that's an excellent question, right? So let me explain a little bit more about how image subtraction works, right? So step one is to measure the point spread function on the image that you just got tonight, right? Then you compare that to the point spread function from your reference image, right? And then you can let's think of that as a simple Gaussian, right? It's not a Gaussian, but let's just for a moment assume it's a Gaussian. Say it was very windy tonight, so that Gaussian has a very wide width, right? Compared to your reference image, where you had a nice narrow Gaussian, the weather was great. So now you want to convert this Gaussian, say with another Gaussian, to be able to degrade that reference image to match your image today and align it very precisely and then subtract it, right? So you can convolve a Gaussian with another Gaussian to match the Gaussian at hand, and you can solve it, right? Now, the challenge is that it's not a Gaussian. The challenge is that the point spread function is a more complicated shape. And so there's an algorithm that we use called ZOGI, which is a paper led by Barak Zakeh from just a few years ago, which outlines in great detail what is actually mathematically the most optimal way to subtract these images. So if you're interested, I encourage you to go read that paper. The last name is Zackay.
The second question is also about the same image subtraction process. So what exactly does REF represent when NEO is the data obtained for newly fabricated instruments, right? So what is the reference that we're taking?
Right. So that's a great question, right? So reference image is basically what we do typically for, say, this Wiki Transient facility, also for Palomar Gattini-IR, is we take, when we first open up the camera and start imaging the sky, we combine some of our best images, let's say at least our 7 best images, and sometimes we do 15 or even 40 of our best images to build a very nice, deep a high quality reference image, right? So that the noise properties, now the noise properties in the subtraction image would be a combination of noise from the new image that we just got and the reference image. But if we build a high quality reference image, then we're only limited by the noise in the new image. So that's why if you build a nice, beautiful, deep reference image by stacking different images, and I just told you about how exciting subtraction can be. Optimal addition is a whole different game as well when it concerns images. And so there are some very nice algorithms again on how to optimally add these images. And that's what we use to build the reference image. And that's what I call REF.
Okay, how exactly is a gamma ray burst affected by gravity? Would it affect the shape or anything?
So the gravitational waves are coming from a different. Okay, let me explain. Let's break this up, right? So this is referring to probably the gravitational wave event from August 17, 2017. So in that event, when the two neutron stars merged and formed a black hole, the excess energy was what was dissipated as gravitational waves, right? So think about gravitational waves as ripples in the fabric of space-time. So when these compact objects merge, so you can think of M1 plus M2, right? So you have a neutron star mass M1, the second neutron star mass M2, and then you have the mass of the black hole. So LIGO can measure all three, but M1 plus M2 does not equal to M3. Okay, there's a small delta, and that delta M, which is M1 plus M2 not equal to M3, that delta M, the difference times c square, is actually the total amount of energy that's dissipated in gravitational waves. Okay, in that, and that has nothing to do with actually the gamma ray burst. The gamma ray burst is being launched because when that black hole is formed, it launches a jet. It launches this ultra relativistic jet. And what powers the gamma ray burst is a combination of external shocks and internal shocks of that very collimated, very high-speed jet that is being launched. So we are talking about things moving at 0.99999, right? So Lorentz factor of 100. So 1 over square root of 1 minus v square over c square, right? That's what your definition of beta is. And so this Lorentz factor is almost 100 here. So it's very, very close to the speed of light.
When you were talking about the classical novae explosions, so what is the process that leads to them?
Another good question. So now we're going back to the white dwarf section, right? When you have a white dwarf, and let's say you have a companion, say a red giant or red supergiant, actually it could be anything, pretty much. Now, when the white dwarf, because it's much more dense and much more compact, it could sometimes you could fill the Roche lobe and you could transfer material. The star could come too close, such that you transfer material in a stream from the red giant onto the white dwarf. Now, when you transfer this material, now the white dwarf is very finely balanced, right, between gravity and electron degeneracy. So when there's this extra material, the surface gravity is very high on the surface of the white dwarf, and you could have this burning. You could have thermonuclear runaway. You could have this material actually burn on the surface of the white dwarf, where you're burning the hydrogen on the surface of the white dwarf. And this burning of hydrogen on the surface of the white dwarf gives you this explosion called a nova explosion, which is about 1 million times the brightness of our sun. So it's quite literally the burning of material that got transferred onto the surface of the white dwarf. And now how much material got transferred depends on the rate of transfer, and it depends on what the quantity, what is the ignition point, right? Because if you wait too long, you'll be burning a lot of material, right? So there's a certain threshold at which that material gets ignited. So that ignition point determines how much material burns, how bright is it, and how long your nova will actually last, right? And initially it was thought that the brightest novae are actually the shorter lived and the slower novae are actually less luminous. But more lately, there have been all types of novae discovered. There have been some really faint novae that are also very short-lived because the white dwarf temperatures were higher, right? Because if the white dwarf is hotter, or depending on the composition of the white dwarf, that ignition temperature would be very different. So you could really get almost any time scale, any luminosity from a classical nova explosion, because it's all about how much material gets ignited and what that ignition threshold is.
Ma'am, you mentioned the disparity between the time of measurement of light waves and gravitational waves. So is that just because of the refractive index of the stellar dust, or is there some other factor involved as well?
There was a 1.7 second difference, right, between when the gravitational waves were detected and when the gamma ray burst was detected. But you have to appreciate that actually light and gravitational waves travel at exactly the same speed. They both travel exactly at the speed of light, right? So this 1.7 second delay doesn't have anything to do with the speed at which they travel. They travel at exactly the same speed, but it has to do with the physics of the launching of the jet. So I showed you the simulation of the cocoon, and what you'll realize is that when that black hole is born, right at the instant it's born, the gravitational waves are released, right? So you detect them right away. After the jet is launched, there's all the stuff that's happening, right? Where the jet is transferring energy to a cocoon, then the cocoon is expanding, then that cocoon is breaking out of the shell of material, right? Because there's all this material around it, and that how much material there is and what the speed of that cocoon is, that's inducing a lag in when you actually see the gamma rays, right? Because you don't see gamma rays until you break out of the surface, right? So you don't see gamma rays at the point that the jet is launched. There's no gamma rays then, right? You only see gamma rays when that jet or the cocoon actually breaks out from the surface. And that induces the 1.7 second lag, and that's in our frame. And if you were actually sitting inside the neutron star merger itself, right, that would actually be longer. So it could be several seconds. So it doesn't have, it's not observational correction. It's actually a physical correction because the gamma rays are not created instantly. And the radio and X-rays are after that shock front interacts with the surrounding medium, right, with the interstellar medium. And that takes another 9 days, right, which is a very long time because you have to wait for that shock front to not only break out, but then interact with the surrounding medium. So the time lags that you see in detecting the photons have nothing to do with the speed of light, because the speed of light is identical to the speed of gravitational waves. It's exactly c, but it has to do with the physical process that's creating or generating those photons.
Okay, thank you, ma'am. Coming to the last question, how do we improve the search for EM follow-ups as soon as a gravitational wave detection is registered in future detectors?
How do we what? Sorry?
How do we improve the search for electromagnetic follow-ups as soon as a gravitational wave detection is registered in future detectors?
Yeah, no, that's an excellent question as well. And, so I told you about the event in 2017, right, where, within minutes, within hours, there was lots of light, right? Now, in 2019, the gravitational wave interferometers turned back on for a whole year almost. It was a little bit short. It was 11 months due to the pandemic. But during this time, there was another opportunity to find more such events, right? To look for electromagnetic counterparts to these gravitational wave events. And while there were many more triggers because the gravitational wave interferometers had become more sensitive, there were no more electromagnetic counterparts found. And what this tells us is actually that if you invert the problem, right? Like what does not detecting any electromagnetic counterparts tell you? It tells you that actually intrinsically the event from August 17, 2017 was an exception. It was one of the most exceptional events, and it's not every event is going to be as luminous and as blue and as bright as the first one. So in order to detect and improve our chances of detecting more and more of these multi-messenger events, in my mind, one of the most important things we need to do is improve our red sensitivity, right? Improve our sensitivity in the infrared bands. Because if you think about it, right, the geometry can play a huge role. If you're just a little bit more off axis, you may not see that blue emission at all. But no matter where you are, because of you're always going to be synthesizing these heavy elements, they'll always have this bound opacity. You'll always see infrared photons, and you're not hostage to we're looking in this way or this way. You're not dependent on what the mass ratio of the two things are, right? Like especially if you think about these neutron star black hole mergers, sometimes that neutron star can just get swallowed whole by a black hole. If the black hole is much more massive than the neutron star, if they're comparable in mass, then you have a much better chance of seeing an electromagnetic counterpart. So bottom line being that for all of these reasons, the last few slides I had were on how do we build even more sensitive infrared detectors, which are both wide field of view and have a larger aperture at the back end, so that they're more sensitive to gravitational wave counterparts. So we have a new telescope that we are building at Palomar called Winter, and that will have sensitivity to neutron submergers out to about 190 megaparsec. So we should be sensitive to that in the fourth observing run, which is supposed to start in the summer of 2022. And that would sort of push the phase space a little bit more, and sort of on the 2027 timescale. That's when I want to build this telescope in Antarctica, which would have exquisite sensitivity in the infrared, because the night sky is about a factor of 40 darker in Antarctica in the infrared than anywhere else on Earth. So even though it's a very cold place and it's very difficult to get to, it's actually a fantastic laboratory for infrared science because of the background being lower, right? It's always a game of signal to noise. Either to be able to detect fainter signals, you need to lower your noise. And the night sky is one that you have to live with, right? And there's an opportunity there to reduce that by a factor of 40. So you can boost your sensitivity to nearly 400 megaparsec for these neutron star mergers by building a telescope in Antarctica.
It was a delight having you with us. Hopefully we can host you on campus as well.
My pleasure.